Something is moving through our solar system that breaks the rules of physics. A 400,000-kilometer jet points straight at the sun, from an object first catalogued as a comet. By all logic, it should not exist. Solar radiation should blow it apart instantly, and yet it does. Harvard astrophysicist Avi Loeb says the phenomenon is extraordinary. Under normal conditions, this jet could never form. Small particles would scatter immediately. Large particles would require forces beyond anything typical comet activity can produce. The paradox is stark. Either our understanding of comet physics is incomplete, or something entirely unusual is happening. Loeb's analysis suggests these limitations vanish if the material is actively expelled, instead of passively sublimated. Comets are supposed to be simple. Ice melts, gas escapes, dust rides along. Tails form away from the sun, pushed by sunlight. Sublimation works for light, small particles, but fails for anything larger. If 3I Atlas's jet were just sublimation, it would be short-lived and diffuse. Instead, it persists, maintaining an almost impossible orientation, even as the comet moves past perihelion. Astronomers initially doubted their eyes. Could this be an illusion, a projection called an antitail? Occasionally, orbital alignment creates sunward-pointing features, but they are subtle and temporary. Not this time. The jet is coherent, stretching hundreds of thousands of kilometers, indicating a sustained, organized source. Over multiple nights, observations revealed something remarkable. The jet wobbles. Bright spots shift in a consistent pattern, implying rotation. The observed wobble period is 7.7 hours, but the nucleus may rotate every 15.5 hours. Comet jets normally flicker randomly, responding to sunlight on uneven surfaces. Here, the motion is predictable, steady, and mechanical, more like a machine than ice sublimation. The physics of particle acceleration highlights the mystery. Tiny particles are pushed easily by gas drag but cannot resist solar radiation sunward. Large particles need forces beyond normal comet activity. Loeb proposes a directed expulsion mechanism. If material is ejected like thrust, both small and large particles could maintain the jet. Importantly, this does not require alien technology. Natural mechanisms like pressurized pockets, structural venting, or exotic ice phase transitions could achieve the same effect. Another clue: the jet remains narrow and columnated. Sublimation usually produces wide, spreading streams. Here, the coherence stretches vast distances, suggesting an organized ejection mechanism. Skeptics argue natural fissures can produce narrow jets, but the combination of rotational wobble, persistent alignment, and sunward orientation is striking. One anomaly might be explained naturally. All of them together strain our models. Chemical observations deepen the mystery. Polarimetry shows unusually deep negative polarization, implying particle properties unlike typical solar system comets. Coma spectroscopy reveals carbon dioxide dominates, while water is minimal. CO2-rich comets exist, but pairing this with a persistent directional jet and unusual polarization pushes 3I Atlas beyond known comet behavior. Mass and size estimates add complexity. The nucleus seems large but not wildly active, hinting at structural or compositional quirks suppressing expected outgassing. Natural explanations remain possible. Subsurface cavities, layered volatile distributions, or thermal insulation could prolong activity past perihelion. Interstellar comets might inherently differ from solar system comets. Formation conditions or exposure to cosmic rays could produce chemical and structural patterns unfamiliar to us, but these require stacking rare conditions, making the combination highly unusual. So what are we looking at? 3I Atlas could be exceptional, or perhaps represents a new class of interstellar visitors. Observations challenge assumptions. How do interstellar objects behave? Can models calibrated on solar system comets apply to objects from other star systems? Each new data point pushes the boundary of what is possible. Every anomaly matters: the anti-tail, the persistent wobble, the directed jet, the unusual polarization, and CO2-dominated chemistry. Individually, these are curious. Together, they form a puzzle that defies conventional comet science. As 3I Atlas approaches Jupiter, each measurement adds insight and defies predictions. We are not ready to claim full explanations, only to map the boundaries of possibility and explore hypotheses that reconcile these extraordinary observations with known physics. Ultimately, 3I Atlas may fit within extreme natural variance, a comet formed under rare conditions. Or it may reveal processes that go beyond conventional cometary physics, hinting at new behaviors in interstellar objects. One thing is clear: 3I Atlas is pushing the limits of what we understand. Its persistent jet, rotation, and chemical quirks challenge everything. Observers must proceed with caution, skepticism, and curiosity. Takeaway: this is not a typical comet. 3I Atlas is an interstellar enigma, a cosmic puzzle traveling through our solar system, forcing us to rethink what is possible. One thing is clear: 3I Atlas is pushing the limits of what we understand. Its persistent jet, rotation, and chemical quirks challenge everything. Observers must proceed with caution, skepticism, and curiosity. Takeaway: this is not a typical comet. 3I Atlas is an interstellar enigma, a cosmic puzzle traveling through our solar system, forcing us to rethink what is possible. Its story is still unfolding, but every observation reminds us that the universe is stranger and more imaginative than any theory can predict. 3I Atlas is not your ordinary comet. Its jet points at the sun like a cosmic lighthouse, twisting and wobbling in a rhythm no ordinary comet should sustain. Every observation challenges our understanding, and yet the data is clear. Something extraordinary is happening. The jet is massive, hundreds of thousands of kilometers long, persistent, coherent, and it rotates. Over multiple nights, astronomers tracked a wobble in the brightest part of the emission. The observed wobble is about 7.7 hours, but the nucleus itself may rotate roughly 15.5 hours. Unlike normal comets, whose jets flicker and shift chaotically as sunlight warms uneven surfaces, 3I Atlas's jet moves predictably, stable, organized, mechanical, almost machine-like. This rotation is more than geometry, it's physics. The wobble indicates that the material is being expelled in a controlled way. Gas drag from ice sublimation cannot keep heavy particles aligned over hundreds of thousands of kilometers. Only a directed mechanism, whether natural or exotic, could maintain the jet. Loeb emphasizes no alien technology needed. Pressurized pockets, structural venting, or exotic ice phase transitions could produce the same effect. Nature, it seems, can sometimes be stranger than science fiction. The jet's stability is equally puzzling. Sublimation jets normally disperse into wide angles. 3I Atlas's stream remains narrow, collimated, and sunward pointing, even as it moves past perihelion. Every night, the jet keeps its coherent structure, defying predictions. Pressurized pockets, structural venting, or exotic ice phase transitions could produce the same effect. Nature, it seems, can sometimes be stranger than science fiction. Even fissures and cavities in ordinary comets rarely produce such persistent aligned jets. This suggests an internal architecture, perhaps channels or conduits directing material like a cosmic hose. Chemical signatures add another layer. Polarimetric data shows deep negative polarization, unusual for solar system comets. Coma spectroscopy reveals high carbon dioxide levels, far exceeding water. CO2-dominated comets exist, but not with such persistent, organized jets and odd polarization patterns. Something about 3I Atlas is different at the molecular level, hinting at formation far from our Sun under conditions we rarely encounter. Mass and size also defy expectations. The nucleus is large but not highly active. Normally, a body this size produces more chaotic activity as ice sublimates. Here, the activity is focused, rotationally stable, and directed, suggesting structural or compositional peculiarities. Perhaps it is layered or insulated, with pockets of volatile material controlling the outgassing. Non-gravitational forces are present. 3I Atlas does not follow a purely gravity-driven path. Small deviations are typical for cometary sublimation, but here, the magnitude and direction of acceleration exceed expectations. Forces act along vectors that do not match solar heating patterns, implying unusual surface activity or a structured expulsion mechanism. This, combined with the narrow, rotating jet, suggests dynamics unlike any ordinary comet. Comparison to other interstellar objects is revealing. Oumuamua, the first confirmed interstellar visitor, accelerated without a visible coma, leaving astronomers baffled. Borisov, the second, behaved more like a normal comet, though with minor anomalies. 3. Atlas is more extreme. Persistent jet, rotation, unusual chemistry, non-gravitational acceleration. Interstellar objects may not follow the templates we built from solar system comets. They could be formed under cosmic conditions far stranger than anything local. Viewing geometry complicates interpretation. Antitail illusions can mimic sunward-pointing structures, but 3I Atlas's jet is too long, too stable, too coherent. The orientation persists even as the comet moves through space. Combined with particle acceleration constraints, conventional sublimation cannot explain the observations. Only a directed expulsion, whether through natural or as yet unknown processes, resolves the paradox. Observational challenges remain. The comet is distant, faint, and small in the sky. Spectroscopy and high-resolution imaging blend light from the nucleus and dust, making detailed analysis difficult. Nucleus size, particle distributions, and composition estimates contain uncertainties. Yet even with these limits, rotational wobble, jet coherence, chemical anomalies, and unusual polarization stand out. 3I Atlas defies classification. Its upcoming encounter with Jupiter may be crucial. Tidal forces could change its rotation, trigger outgassing, or reveal internal structure through orbital shifts. These measurements will help refine size, density, and mass estimates. But even without them, the comet's existing anomalies, CO2-rich chemistry, rotating stable jet, non-gravitational acceleration, and antitail structure, already challenge conventional physics. So what does this mean for interstellar comet science? Perhaps rare natural processes stacked under unusual conditions explain 3I Atlas. Or perhaps interstellar objects inherently differ from solar system comets, shaped by exotic formation environments, cosmic rays, or collisions across billions of years. Either way, 3I Atlas forces scientists to question Earth-centric models. Cosmic context matters. 2025 has already surprised astronomers. Gamma-ray bursts, magnetic turbulence near black holes, and extreme comet diversity. These events remind us that the universe is unpredictable. Interstellar comets like 3I Atlas are windows into alien chemical and structural diversity, archives from distant star systems, carrying records of billions of years and light-years of distance. The object may be an extreme natural comet, or it may reveal physical processes previously unseen, pushing boundaries of what physics allows in interstellar objects. Its rotation, jet, chemistry, and dynamics invite careful skepticism, but also imaginative exploration. Observations continue, models will adapt, and scientists will assess whether it fits within extreme natural variants or something entirely new. Every anomaly tells a story. the wobble, the anti-tail, the directed jet, unusual polarization, CO2 dominance, non-gravitational forces. Together, they reveal a cosmic puzzle unlike anything seen in the solar system. As humanity observes 3I Atlas, we are reminded that discovery is iterative. Every observation challenges assumptions, expands knowledge, and forces us to rethink physics under alien conditions. Whether 3I Atlas fits existing frameworks or reshapes them, it proves one thing: the universe is stranger and more imaginative than any theory predicts. In the cold, dark space between stars, interstellar objects drift silently. They carry stories written over eons, waiting for curiosity, instruments, and patience to uncover them. 3I Atlas is more than a comet. It's a cosmic enigma, a puzzle of physics, chemistry, and motion. Its mysteries may push the limits of our understanding, urging scientists to explore, question, and imagine. And as we watch, we glimpse the universe's vast, intricate, and unpredictable nature. The jet points at the sun. It rotates. It accelerates unexpectedly. Its chemistry is alien. Its motion defies gravity. 3I Atlas reminds us that space does not conform to expectations, and the cosmos holds more surprises than we can predict. The story is far from over. As 3I Atlas moves through our solar system, every new observation could rewrite what we know about interstellar visitors. And one day it may finally reveal whether it is simply a rare natural comet or something that stretches physics to the edge of imagination.